these geometric models. So given a geometric model and a possible, well, a pair of position and direction of angles, and the given formula phi, sorry, well, this is all that's in the geometric model. So again, the geometric model has the positions which we can assume fixed, the angles which we can assume fixed, and so what can possibly change is the directions of vision. So suppose that we have given them, and we are given a formula. Sorry, this is not epistemic. Again, oh, I need to fix this. It's a formula of our language, to determine whether the formula is true in this model or not. Okay, so I'm sorry, some of my slides are mixed up with previous slides. Now, this problem is decidable, and well, it is decidable within exponential space. This is by brute force translation of this problem into the first order theory of the reals, which we know from Tarski already, that it is decidable. Of course, Tarski's procedure based on quantifier elimination led to non-elementary complexity, but it was later on refined, and so it's still not known what is the precise complexity, but it's sitting somewhere in exponential space. So then one can solve this problem by this reduction. But of course, this is, well, first, this is sort of inelegant, and second, it's most likely not optimal, and we'll see that it's not optimal. So then we are looking for better, more elegant, and more optimal solutions of this model checking problem. Okay, now one more interesting point to make here is, and which is related to how we solve the model checking problem, is by translating this language that I presented here into another one that's the PDL, propositional dynamic logic flavor language. So all the epistemic relations will now be turned into dynamic operators. And the idea is very simple. So here is the grammar. It's, again, those of you who know propositional dynamic logic, then there will be very little new to see, but still something. So first, the atomic propositions are again interpreted. That is, A sees B. And then in the repertoire of programs, we have all the standard regular operations as we have them in PDL. But in addition to that, we have this specific operation, which is the agent turning at a certain angle. Okay, that is, with every agent, we associate this, well, atomic program A. Okay, and then we also have a test whether a formula phi holds. So using this language, this repertoire, we can actually translate the language of VBL with all the epistemic relations into pure like language. And so here is the idea. If we can translate the individual knowledge operator, then the common knowledge will come easily by using iteration. So here is how we translate the individual knowledge for the agent A. So this will be a composition of programs that look like this. So we have a non-deterministic choice. We test whether A sees B1. And if A sees B1, then nothing happens. B1 cannot turn, cannot move, because A sees B1. But if A does not see B1, then we allow B1 to turn freely around, because the agent A will not see this, will not notice this, and so that would not affect the knowledge of the agent A. That's the whole idea. So that, well, in this case, A sees B1, so that we don't touch B1. But A does not see B2, so that we can move B2, see, and that will not change the knowledge of the agent. So that's the idea. And we do that with every other agent, so that eventually we compose all these together, and then we produce one big program that represents the knowledge of the epistemic relation of the agent. Okay. So once we have done this with the individual knowledge, then common knowledge is obtained by just taking the arbitrary compositions and then iterating. Okay. So, well, again, to cut the long story short, using this representation, PDL style of representation of our language, we organize the an algorithm for the model checking problem that eventually runs in polynomial space. And it's not difficult to see that P space would be a lower bound because there is a polynomial reduction of the QBF subproblem. This is the quantified Boolean formulae logic. If you don't know it, ignore it. To the model checking of this logic. So then we have matching lower and upper bounds so that this is precise complexity P space. Okay, so the algorithm, here it is, it exists. And I will not go in details, but it uses divide and conquer sort of programming technique. Yeah. Okay, so much about model checking. So p-space, and this is optimal. Now for the satisfiability, the problem again is this. Given a formula, now we can think that it's in the PDL language, so in the PDL VBL language. And we're asking the question, is this formula satisfiable or not? That is there a geometric model that would satisfy? Okay, so how do we solve this problem? We solve it with lots of guessing and then testing. So you know that if you have some experience with p-space, you know that you're allowed to do lots of guessing for as long as you stay within polynomial bounds, and then check your guesses. All right, so here we go. First of all, we non-deterministically guess vision sets for all agents. So again, we are after a geometric model that would satisfy our given formula. So we will not generate the precise model, but we'll generate the finite abstraction that is the vision set model. And for that, we need to generate the vision sets, the particular sets of visions for each of the agents. So we just guessed them. They are finitely many, so we guessed them. Now, once we guessed, then we need to check that these are indeed geometrically consistent, because they need not be. And here we need to do some honest work here. That is, we need to now translate this into the first-order theory of the reals and check the geometry and see whether this works. But now we are sitting in the existential fragment of the first-order theory of the reals, which is decidable in p-space, and that really helps us. Okay, so the reduction is not to the full theory, but to the purely existential fragment. Okay. And so that once we have guessed and checked that it works, then we guess non-deterministically a world in this model, or in this vision-based model, where our formula might be satisfied. We check that using the model checking algorithm, and we are done. So that's in a nutshell how the satisfiability problem is solved. So again, in summary, the logic is decidable and it's reasonably low complexity, p-space. Okay, now, one can extend this framework in various ways. I'll mention just a couple of extensions here. One is with public announcements. Announcements of the type that, let's say, an agent A can say, I see B and C, but I do not see D. And so the agent A announces these to everyone around, that is, all agents hear this. And so that would make an update of their knowledge. So their knowledge changes based not on what they see, but also on what they have just heard, assuming this is truthful, which is standard assumption. So that adding these public announcements in the language will naturally, well, presumably boost the expressiveness of the language, but it doesn't really do it in a dramatic way, so that essentially all the procedures, model checking, and satisfiability testing, they would remain valid. Well, they have to be adjusted, of course, but they would remain working in the same complexity, so that all works nice. Oh, sorry, I'm not quite correct. So satisfiability is now in exponential space because the guessing is a bit trickier, so that we don't have it yet translated into the existential fragment of the first-order theory of the field of reals. But the rest works fine, so that is still decided. And then, of course, it would be natural to add obstacles. So in real world, there are lots of obstacles so that the agents do not see everything that's in their sector of vision. So adding obstacles, of course, well, it adds a technical overhead there. But again, it's controllable. So the finite abstractions still work. It's just computing the vision sets have to take into account the obstacles. The model checking algorithm can be accordingly modified, so it still works in p-space. And again, the satisfiability is somewhere between these two complexities, so we don't know exactly where it sits. Now, in conclusion, so first, a brief summary of what I've done. So I've presented to you a framework for visual-epistemic reasoning of many agents, which is sort of illustrated with a metaphor of cameras, vision cameras. But again, you should see beyond that, I hope. Right, so I've given you several different semantics, and I've also shown how this language can be translated into a purely sort of operational language, PDL style of language, which can be used to optimally solve the model checking and the satisfiability testing problems. The main open problems that remain here are, apart from, well, identifying the precise complexities when we extend the language, but the main open problems from logical perspective are to characterize in a more precise and explicit way the expressiveness, and eventually to obtain explicit, complete axiomatizations of this logic. And for the more ambitious proof theories here to come up with a real, true, practical proof system of, let's say, sequent calculus for one of these. It would be really very nice, would it not? Even though we have algorithms that sort of kill the joy of using deductive systems, but this would still be something very valuable, of course. Okay, so let me see what more do I want to say about this. Nothing more on this. So the final slide would be some suggestions for future work, where I'll stop here. First of all, of course, our cameras were in the plane, but in reality, things take place in at least 3D space, and in science fiction, even in more than 3D. So that next step would be to move to the 3D space. So where, our cameras will see what we can call a cone of vision, or some sort of generalized cone of vision. Again, there is obvious technical overhead that comes with this, but we are still sitting in the first order theory of the reals, so that things will be decidable, and eventually, if we don't care about complexities, then we can just translate everything there and then have it done, but we'd like to do it in a more elegant and more efficient way, and so this is where the main problems come, and so that, things become more complex, but we can still show that the model checking and the satisfiability without obstacles remain space complete. And then next natural extension would be to let agents move around in the plane, so that not only turn but also move. And every movement in the plane can be reduced to a translation followed by a rotation, so that that can be captured geometrically, and then again with the due technical complications we can still organize algorithms to solve the model checking and satisfiability problem. But again, there is a big problem about the complexity here, because we don't know whether finite abstractions will still work the way they work in the plane, for reasons that I don't have time to explain. So that we don't have yet optimal complexity results there. Now, lastly, what I've presented here is a concrete and looking probably somewhat artificial framework, but my purpose in this talk was to use this framework to illustrate first, the very idea of combining visual and other reasoning into a logical system, in this case visual and epistemic reasoning, because again, the visual information that we receive, we naturally use to extend, to modify our knowledge. So, and then we can then use it for further purposes, for instance, talk about agents, to act, to plan their actions, to compute strategies, and so on and so on. But so that's the future story. So the point is that visual and epistemic reasoning, they go hand in hand. And they interact with each other both ways. And so this is what I've illustrated here. So that the general problem that arises here is, first, how to represent in the best possible way, in a symbolic way, the relevant visual information that comes our way, or the way of the agents, and ignore the irrelevant information. What is relevant, what is irrelevant, how to select and to represent the relevant one, ignore the irrelevant one, so that we can not just reason theoretically about, for instance, logical validities, logical consequences, so that is do logical reason, but also be able to compute it. And so I think that is still a big challenge, and it's a fairly interdisciplinary challenge. It involves computer scientists, logicians, philosophers, like I am one of them now, and so on. So anyone who would be interested in following on this, you're most welcome to talk to me while I'm here during this conference. Thank you for your attention. Sorry?
What happens if the set of agents is not fixed?
Well, okay, if the set of agents is not fixed, then in a sense you cannot capture that in, at least in the type of languages that I've presented here. I mean, you could think of of saying something that some agent can see something. But, okay, so we haven't looked at that yet. I think it's a very relevant, meaningful question because things in practice are dynamic. Agents come and go. And we want to reason about, let's say, shared information or about accumulated information or knowledge that they acquire. But we have not looked at that yet. So you can think that there is one, I mean, simplify things. There is one universal set of agents. Some of them might not be present all the time. They may come and go. But the universal set of agents is there, and we are reasoning about it. So that's the best answer I can give you now.
Yes, I'm a philosopher, so maybe I may ask a rather philosophical question.
Please do.
Your individual agent knowledge operators, are they S5 modalities?
Yes, they are.
You have
Yeah.
all these problems of logical omniscience. And in addition, you also assume something like positive and negative introspection when it comes to seeing. If agent A does not see B, then A knows that A does not see B.
Yes.
These are rather strong idealizations.
Indeed.
So would it make sense to have something like awareness operators?
Yes. Yes. No, absolutely. Yes. It's a very fair question. We have made this idealization that knowledge here is S5. And I would say, okay, this is justified when we talk about knowledge in very simple, concrete situations as it is here, not knowledge in general. And if you want, even if you think of this as knowability, rather than saying the agent knows phi, then the agent can know phi if the agent looks into it and so becomes aware of all that it involves and then opens his or her eyes, literally. So, but otherwise, in general, I completely agree that if one wants to build up a more sort of realistic picture of more human agents that, well, may see many things, but not aware of everything that they see, which is almost always the case, then things, of course, will become rather more involved. But yes, that's absolutely a meaningful point.
Normally you expect one object to be easier to do than such viability.
That's an interesting point, and over the years, I've swayed my opinion on this. And I'll tell you, indeed, usually it is the case that model checking is of lower complexity, or not higher complexity than satisfiability. But you can design logics, well, if you want artificially, where the satisfiability problem would be sort of trivially, or just linearly, or even constant. So, for instance, every formula is satisfiable. Yesterday, someone gave a talk saying that, yes, I think it was in Marcel's. Yes, so there was a story where it was about probabilistic propositional logic of a kind that everything was satisfiable. So satisfiability is trivial. Model checking is not. So that it's not always the case. Again, there are, and it's not only artificial, but there are also more or less natural cases where the satisfiability is of lower complexity because it does not actually require checking in a model. It could be that no formula is satisfiable. I mean, put it this way, you can design a logic where nothing is satisfiable. So, but yeah.
Valentin, another. A more kind of industry-like question.
Good.
So
You are a representative of the NSA, or so I need to know how to answer.
The thing is, if you want to, have you talked to the guys doing robotics? Have you talked to them to see which bits of your logic they actually like or dislike? Which bits they want to do probabilistically? Which bits they want to do symbolically? Because, you know, I saw there was an N robots there, right? So
Yeah, yes.
it is important to kind of bring the AI guys into this fold too.
Indeed.
I mean, I know that in some Brooklyn, for instance, have been, I mean, all the guys playing robot, soccer robot stuff, they must have the same sort of stuff about seeing the other agents and wanting not to. What happens there?
Yeah. So, okay. So what happens is this. I'll actually answer by referring to your talk. You said that well, logicians and computer scientists should be talking to each other about model type theory, but shame they don't do. So, okay. Now, to be a bit more serious, this work we first presented at this AMOS conference, which is Autonomous Agents, Multi-Agent Systems, huge conference that involves from pure theoreticians to pure practitioners. And so there were some people coming from the other party to that talk, and they expressed some interest. They say, yes, that's nice, that's interesting, but we kind of, well, don't see how we can use it now. So, of course, that doesn't mean much, but the point is the two worlds haven't met yet. Or put it in other words, we are working for the future here. The future hasn't come yet. I mean, the type of problems that people would solve that would, for instance, that could use this to design an intelligent surveillance system, now I'm being serious, these type of problems, they already do exist there, but they solve them on a sort of low-tech ad hoc basis. There is no sort of, you know, high-tech approach yet, for reasons that we know.
I was wondering about the expressiveness of the logic when you add obstacles or occlusion, because I think occlusion is basically clipping to obstacles. But when you are talking about betweenness and co-linearity, you're kind of assuming that the agents are transparent. What happens when there's occlusion or obstacle? How agents see the obstacles? Can they tell this is the vertex of an obstacle or this is the edge of an obstacle?
Yes. No, very good question. So, of course, this goes more into a practical direction, but since a couple of years ago, while I was still a computer scientist in my previous life, I had students actually implementing, because I supervised a project course, so I had students implementing this with obstacles, and so things practically look quite simple. So, so the question is, for instance, I'm an agent, and you are a point of interest, right? And so whether I see you or not depends on, well, two things. First, whether whether you are in my angle of vision, and second, whether there is an obstacle between you and me. So that if you can formalize this, you need to extend the language ad hoc, saying that, well, so there is an obstacle between that you can say using, well, these sort of tricks. But with a little extra work and with suitably extending the language, you can say that, yes, A can see B in possibly the presence of obstacles so that A cannot see B. Of course, things are a bit more complicated because if, for instance, if you want to know whether an agent can see a point that sits behind obstacles that are not necessarily convex, then you need to do extra geometric work. But that really goes beyond what I'm saying. So that I would say this is a very relevant question, but it goes more into the pragmatics of the story than into the purely logical issues that arise there.
Okay. So we'll finish the section. So let's thank our speaker again. Thank you.
Thank you.